Welcome to chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at how you determine empirical formulas. Now, discussion of empirical formula starts with the idea of understanding what a formula is. So, what does H2O actually mean? Does it mean that you have 2 moles of hydrogen for every mole of oxygen? I mean, because it does mean, obviously, you have 2 atoms of hydrogen for every 1 atom of oxygen. But does it also mean you got 2 moles of hydrogen for every 1 mole of oxygen? And the answer is yes, always. And that's critically important to what we're doing to find the empirical formula. So formulas are not only ratios of atoms, they're also ratios of moles. What they're not is ratios of masses. So just because water is H2O doesn't mean you have 2 grams of hydrogen for every 1 gram of oxygen, because oxygen and hydrogen don't weigh the same. Now, a formula then is a ratio of atoms, but more importantly and useful to us, because it's very hard to count atoms, but we can weigh something and from that determine the number of moles. And formulas are ratios of moles. You do have 2 moles of hydrogen for every mole of oxygen in a water molecule. Now, the empirical formula, and that's what we're going to be looking at here, is the simplest whole number ratio of moles of the atoms in a substance. So it's the smallest whole number ratio of atoms in a substance. Now, the empirical part of empirical formula refers to the fact that it's an experimental method. So scientists had to come up with some way to determine what the molecular formula of a substance is. And the first step in that process is determining the empirical formula. So it's really the first step that we're going to look at in a 2-day process to find out how we know what the formulas of molecules are. So the first thing we do is we find out what the empirical formula is. Now, if you take a look at the different formulas that are down here, which of the following are actually simple whole number ratios? Because some of these are molecules, and some of these are empirical formulas, and some of these are actually both. So remember, if it can be reduced, it's not an empirical formula. So as you go through the list, water, that's a 2 to 1, that can't be reduced. NaCl, that's 1 to 1, that can't be reduced. C2H6, that can be reduced to a 1 to 3. We can divide both of those by 2. But NO2, 1 to 2, that can't be reduced. H2SO4, you see a 2 and a 4 there, but remember it's a 2, a 1, and a 4, so that can't be reduced. C6H12O6 can, and the last substance, N2O4, that can be reduced because you can divide both of them by 2. So remember, some substances are empirical formulas as a molecular formula, like water. Its empirical formula is H2O, its molecular formula is H2O. Other substances, like glucose, which is listed here, that substance, that's its molecular formula, but its empirical formula would be C1H. Remember, divide everything by 6 here. They're all divisible by 6. H2O1. So that would be the empirical formula of glucose. Now, to find empirical formula, really you need to understand that what we can actually measure in the lab experimentally is how much things weigh. And the first step then is to get the mass of each element. But this is usually given in any problem that we're looking at. So if you actually read the question, they're going to directly or indirectly give you what the mass is of each element. That's the experimental part. And remember, you can't do the experimental part, so that has to be provided in the problem. Now, one way that it'll look like it's not telling you the mass, but it really is if they tell you the percent composition. So what percent of the sample is hydrogen, what percent of the sample is oxygen, and so on. Remember, all you really need to do is get rid of the percent sign and put a gram sign there. Because if you had a 100-gram sample, 16% is hydrogen. If you had a 100-gram sample, then that would be 16 grams for a 100-gram sample size. And you can pretend it's any sample size. I'm going to pick 100 because it gives me easy math. So 36% hydrogen and 64% carbon, we'd use 36 grams of hydrogen and 64 grams of carbon. And yes, we could assume something other than 100 grams as a sample size, but that would make harder math. So we're going to keep it nice and simple. Now, formulas aren't ratios of masses. What they are is ratios of moles. So your next job is to convert from masses to moles. And that's why empirical formula is a part of this chapter, because we just looked at a process for getting from the mass of a substance to a mole of a substance. And at this step, one thing that's important here, notice it's in red. Don't worry about significant digits. Actually, rounding to correct significant digits can make the process a little bit harder. So just write a few extra digits when you're doing the math here. So you've got 36 grams of hydrogen, and we want to change that into moles of hydrogen. Remember our process. We want to get rid of grams, that goes on the bottom. We're looking for moles, and we can, by our flow chart, go from grams to moles in one step. That's the molar mass step. So we look on the periodic table, it says hydrogen is 1.0, and remember it's always the mass of exactly 1 mole, so 1's going to be with mole. And remember, don't worry about diatomics and Hahn-Figl right here. We're talking about atoms of hydrogen and oxygen and so forth. So in this particular case, if I had 36 grams of hydrogen, that would be 36 moles of hydrogen. And if my calculator said 0.111, I would write a couple extra 0.111s there. Now, the last step is to get it to small whole numbers. So we have a valid ratio of moles, but it's not going to really look like a formula. So really what I recommend is you first make it look like a formula. So if we had 1.2 moles of carbon and 4.8 moles of hydrogen after we converted our mass to moles, write it like a formula. And you're going to put your mole amounts in that subscript spot where we would normally put the subscripts in a chemical formula. So it'd be C 1.2 H 4.8. Now, we need to keep that ratio of 1.2 to 4.8 because we can't change that, but we need to get it to whole numbers. The fastest way to do that is divide by the smallest. So in this case, 1.2 is smaller than 4.8, so we're going to divide them both by 1.2. That's going to always make this one 1, and then this one is going to be some number greater than 1. So it's going to get rid of our goofy less than 1 fractions if we divide by the smallest. And 9 times out of 10, at this point, you're done. Like in this case, there's 1 carbon for every 4 hydrogens. It's a 1 to 4 mole ratio. But there will be instances where you won't get exactly a whole number. So if you get 1 and 2.01, that's basically 1 and 2. But if you get 1 and 2.5, I mean, that's nowhere near 2. It's nowhere near 3. You can't just round that to 2 or 3. So we need to maintain the ratio, but we need to get whole numbers. So sometimes you have to multiply, typically by 2 or 3. And it's fairly rare, but it does happen. So let's look at a couple of examples of what we're looking at here. So if we have 0.029 moles of X and 0.039 moles of Y. And remember, this is the result of changing our masses to our moles that were given in the problem. So we're going to write it like a formula, then we're going to divide by the smaller, and then we're going to look at what we get. In this case, we get 1 and 1.34. Well, this is pretty close to 1.333, which is a third. Well, if you triple a third, you get a whole. So this is one where we would want to multiply by 3 to get to whole numbers. And that would keep the ratio, but now give me whole numbers. So if I multiply both of those by 3, I get x3, y4. That would be my empirical formula. Next problem, if you got 0.009 moles of X and 0.006 moles of Y, same thing. Write it as a formula, divide by the smallest, and see what your calculator gives you. In this case, notice you're at a half. Doubling a half would give you a whole. So I'd multiply both of these by 2, and I get x3, y2. Couple other examples. Same idea. Write it like a formula, divide by the smaller, see what you get. Once again, it's a half, so I'm going to double. I'd get x2, y5. Now the last one here, sometimes you get very small numbers because masses in small samples are small. But it's no different. We put the two numbers in the subscript spot. We would look at them and decide, okay, 2.4 times 10 to the negative fourth is smaller, so that's what we're going to divide by. And the x would become 1, and the y is going to become 3.04. Now that's not close to a third or a half. That's actually really close to 3. So in this one, we're already at our whole numbers. We would say it's x1, y3. So that's some examples of that last step. Write it like a formula, divide by the smallest, and if you have to, double or triple. But the doubling or tripling is fairly rare. Now here's an example of what we're going to be looking at with this. So we've got an unknown gas, because remember, we don't know what the substance is. But what we can do is experimentally is do an analysis and find out how many grams of each element are present. So we've got 43.2 grams of carbon and 115.8 grams of oxygen. Step 1 is done. Remember, masses are typically given, or they're given as percents, in which case you can erase percent and put G in there given. Next, formulas aren't ratios of masses, they're ratios of moles. So what we're going to do is take our grams of carbon and our grams of oxygen and convert them into moles. So simple one-step dimensional analysis. We don't want grams of carbon, we want moles, and it's the mass of 1 mole off the periodic table, which is 12.0. So we're going to get 3.60. And remember, if you need to, or if you're given a couple of extra digits, keep them. I mean, if the calculator gives you 3.6, you're kind of stuck with 3.6. But if you got a few extra significant digits, it makes it a little bit easier to see the whole half or third in that last step. Now we do the same thing with oxygen. Oxygen molar mass is 16.0. So when we divide it out, now we get 7.24. Now, step 3 is to get whole numbers. So we write it like a formula, divide by the smallest, and see what we get. And in this case, we get 1 and 2.01. That's basically a 1 to 2 ratio. And that is our empirical formula. And remember, what we've looked at today is our first step in finding the molecular formula. So we're not done. Next, we're going to figure out how we get a molecular formula as well.